Hey everyone, this is Dr. Anna, and today we're going to talk about the second module of historical geology, rocks, fossils, and time. If we think about the rocks, remember in physical geology we have learned the three kinds of rocks, the igneous, sedimentary, and metamorphic. I hope you remember that. Igneous, sedimentary, and metamorphic. Now, in historical geology, I put the title of this slide as sedimentary rocks. Why? Because the igneous and metamorphic rocks do not tell us too much about the environment. However, the sedimentary rocks are extremely important because they will talk to us about the Earth's past environments. They are very useful, and I call them reading material. Like when you first start reading books, you have to learn the letters, am I right? But here in historical geology, we'll have to learn about the sedimentary rocks, which are the letters of historical geology. So this way we can add together the puzzle of the Earth history. What are those letters or tools in historical geology? We have to learn about the sedimentary rocks, and the ones we have to know is the color, the texture, grain size, sorting, the shape of the grains, sedimentary structures, and finally the maturity. It's really important that you go through this and you understand every one of them, so you will be able to look at your sedimentary rock set and characterize them as I ask you. So don't just take it out and just Google the information. Go through the slideshow and learn about it. So the first thing is the color. And remember in physical geology, I told you a couple of times that the color is not defining the type of rocks, because in sedimentary rocks you can have the same kind of rock with very different colors. So when you name the rock, the color is not meaningful. But when you think about the formational environment, it is extremely important because it will tell us about the depositional environment, like the oxygen level, what kind of water depth, and so on. So this here is a slide showing you a picture right here, which is basically the relationship between the rock color and the depositional environment. So when your rocks are really dark and black colors, deep dark black colors, they normally form in a deep ocean environment, deep water environment, or it could also be in the coastal swamp. If it's getting lighter, it's getting closer to the terrestrial environment or the continental environment, and the color therefore is becoming lighter because you have more and more oxygen around. And when it's really brown, light, yellowish, reddish, or even lighter colors, that just means that these rocks formed on the continent where there is a lot of oxygen exposure. So therefore it's really important to understand that the form of the iron in the sedimentary rocks is depending on the oxygen exposure. So when you have an oxygen poor environment, the iron will be a ferrous iron 2+, and it will produce dark or greenish colors. On the other hand, when you are on the continent and you have oxygen-rich environment, the iron will become ferric iron, Fe3+, and that will produce hematite, therefore red, purple light, sometimes yellow colors. So the color of the sedimentary rock is very, very meaningful in terms of oxygen level and sedimentary environment. I'm going to go through a little bit more detail. So when your rock is black or dark color, that just means that there is no oxygen in the sedimentary depositional environment, and that just a lot of the time also means that in this area there will be a lot of undecayed organic carbon. Means that when you have any kind of living thing which comes down to this level, there is no oxygen which actually decays it, so therefore it stays undecayed. Normally these are the rocks which will produce oil or coal for us, so it's very, very important to find this kind of environment. Most of the time this means deep water or coastal swamp. Coastal swamp will produce very similar environment. So when we have this kind of environment, like oxygen poor, the very characteristic mineral here is going to be pyrite, and you also, if you hit the black rocks with something, black sedimentary rocks, I should say, with a hammer, of course your piece is very low, so don't do it. And then smell it really quick, you will have that rotten egg smell, which is the hydrogen sulfide. And that just means that this rock most likely a source rock for coal or oil. Now, if your sedimentary rock is red or light color, that just means that it was formed in near surface environment and there is a lot of oxygen exposure, lots of oxygen present, which completely decays all the organic material. In this environment, all the organic material is decayed completely. There are no undecayed organics present, and therefore the oxygen will make the rocks to be reddish, light, yellowish, and the reddish color always means that there is iron, like hematite or limonite, which is also iron oxide present in the rocks. Now the second thing is the texture, and the texture basically is what you see when you look at a rock. You will see the shape and arrangement of mineral and rock pieces or particles in it. Here are the parts of the texture. The A is the grains or the larger particles. Then between the grains you have the finer particles, which is what we call the matrix. And then the part which you don't see is the cement, which is basically chemical precipitate. So here is a picture, you know, the clasts, which could be mineral or rock particles. You can have the finer grain area, which is the matrix, and the one which you cannot see but it's there is the cement, which is most likely chemical precipitates like calcite, quartz, and so on. Now the third one is the size of the grains, and of course the sorting is important, and we have to talk about it here. This is the Van Wert scale. Basically when you shake your material, it will stay up on the different size scales. And we didn't learn this in physical geology, and I don't really make you to memorize this either. So what you will have to know is the gravel, which is larger than the sand, which, remember, the sand is 2 millimeter and 0.063 millimeter. And if you divide the 1 over 16, it's going to give you the 0.063 millimeter. So that's the sand size, and this will make sandstone. And everything which is larger than the 2 millimeter is going to give you the conglomerate or the breccia. So the next one is the silt, and the silt is 0.063 and 0.005 millimeter. If you divide the 1 by 256, then it's going to give you the 0.005 millimeter. So the silt will make siltstone. And if the sand size is less than 0.005, so the 0.005 is larger millimeter, then it's going to be clay. And the rock which it will form is going to be shale or mudstone. So this is the size, and then the sorting. So depending on what kind of environment the sediment is settling down, it will have different grain size. So it could go all the way from very well sorted, which means every single grain is exactly the same size, to a very poorly sorted, which means that you have every kind of grain size present at the same time. If you wanted to make a graph about the grain size and the frequency of those grains, then you can look at this one, which is a very well sorted sediment, and you can see that if you plot the grain size against the frequency, then when the sandstone is well sorted, then every grain is going to be about the same size. On the other hand, when the sand is poorly sorted, you will have every kind of grain size, and the amount is about the same. So that means every grain size is represented in the sample. So what do you think? Which picture here shows very well sorted sediment versus poorly sorted sediment? Yeah, this one, if I number it, 1, 2, 3, 4. Okay, so the least sorted is going to be the number 2. This will be more likely a glacial environment where you have every kind of grains pulled together from the different mountain. And this here is very similar. It could be an alluvial fan, which means that the the river brings down every kind of grain size from the mountain. Now, this one, the number 1, is a very well sorted. In this one, every grain size is the same. It's a beach sand. And same here. This here is well sorted. Make sure that the fact that it's different colored minerals will not mess you up. The grain size is the same, but the color of the grains are different. So the number 1 and 4 are well sorted, and the 2 and 3 are not very well sorted at all. Okay, so the next one is the shape of the grains. And basically we're talking about the roundness of the grain. So if you look at the individual grain, then you can see that this one here is pretty well rounded, like this one too. On the other hand, if you come down here, most of the grains are very angular, means that they didn't get rounded. So we're also talking here about the sphericity, so the roundness of the grain, and how closely the grain is approaching the shape of a sphere. But of course, it also depends on what kind of rock is the grain made of. Like if we have high sphericity rocks, such as marble or granite, then from angular, when it becomes rounded, it will become more like a sphere. Like that, I guess that's why they call those stones you can buy marble. But if the sphericity is low, like we're talking about well-layered sedimentary rocks or metamorphic rocks, most likely it will be elongated even when it's the most rounded, because they're just not the type of rocks which can make marbles, if you will. Most of the time, geologists use a chart like this where everything is together. So you can compare the sediment in your hand. I don't have enough to give every one of you one. But if you see, we can go from clay all the way to pebbles. You can look at the rounding at the same time, the sorting. So this is a really helpful tool when you are a geologist. So if you do become one, you will have one for sure. I guess I'm going to stop right here, and I will continue it in the next segment.